Welcome to Group 1's presentation on Sun observation. The mission description of the satellite is to investigate and observe the solar atmosphere and the Sun's outer layer through atmospheric sampling and measurements of the heliosphere and stellar atmosphere of the Sun. It may serve as a main source of solar data and for space weather prediction. The satellite will orbit at Sun-Earth L1 Lagrange point, giving an uninterrupted view of the Sun. For the DRO, it is listed on the left side on the table. The satellite would be fitted with instruments to carry out measurements as intended. These instrumentation should be sufficiently able to measure helioseismology, solar atmosphere remote sensing, and also solar winds. The satellite moves around the Sun in step with the Earth by slowly orbiting around the first Lagrangian point, where the combined gravity of the Earth and Sun keep the satellite in an orbit locked to the Earth-Sun line. The L1 is approximately 1.5 kilometers away from the Earth's surface. The satellite will have an uninterrupted view of the Sun there. The operational mission is divided into three main phases: the launch and early orbit phase, the transfer trajectory phase, and also the halo orbit phase. For the purposes of orbital mechanics calculation, a simplified two-body problem would be used to calculate delta V1 and also the orbits involved. Here we assume that the point L1 is a point mass. The first phase, the launch and early orbit phase, have an orbital velocity of 5.29 kilometers per second. The transfer trajectory phase, for transfer trajectory insertion, will need a delta V1 of an increase 4.748 kilometers per second. The time taken for the transfer orbit will be around 40 days. The halo orbit phase would need, for halo orbit insertion, would need a delta V2 of an increase of 0.371 kilometers per second. For the fuel requirements, there are two. The transfer trajectory insertion would need a propellant mass of 1.37 kilograms, and the halo orbit insertion would need a propellant mass of 0.31 kilograms. The propellant used would be on board the satellite itself. For the ground control station, we'll use the Deep Space Network of NASA, which would primarily provide telemetry and control from three ground control stations in Madrid, Canberra, and Goldstone. The visibility of the satellite by the Deep Space Network affects the resulting transfer orbit and daily launch window chosen for the satellite. The DSN coverage ranges from 55 to 91 minutes. For the launching of DRO, the multiple stage rockets, it needs to achieve low Earth orbit and transfer orbit, able to launch a mid-sized satellite into low Earth orbit and an Earth escape trajectory, launch at a suitable launch window for optimum transfer orbit to L1, launch from a suitable location, and budget-friendly launch procedure. For the launch windows, from literature, we found there is two launch windows in around May and in around November, and we selected launch on November due to the low chance of precipitation and less average monthly rainfall in the launch site when compared with the month of May. For the launch vehicle, we have a variety of launch vehicle we analyzed. We finally chose Falcon 9 as it fulfills all the required DRO. For the launch site, we chose Cape Canaveral because it can take advantage of the Earth's rotation as it is close to the equator. East of the launch site are regions of sparse population, and it is a proven launch site with adequate facilities as it is the home base of the launch vehicle operator, in this case SpaceX. For the separation procedure, roughly it would be like this. It will start with liftoff, followed by main engine cutoff and stage 1 separation. The first ignition of second stage will put the spacecraft into a preliminary parking orbit, and the fairing would be jettisoned. At this point, there is a thermal roll where all surface of the satellite would be exposed to the sunlight for even temperature distribution. The second ignition of second stage would put the spacecraft into a transfer trajectory phase. The satellite separation would occur once the DSN network is back online and could have constant communication with the spacecraft.
For the structure, we do a comparative study to show how this is the exploded view drawing and review drawing of the spacecraft. And then the material used is mainly aluminum to cope with the cold weather. The structure uses a PLM or SVM interface, which are maintained at 20 degrees Celsius. The antenna composed of a 0.8 meter diameter and several associated mechanisms, and it is rigidly attached to the spacecraft and is only released after the aspiration process. And then for the attitude control system, we established the design requirements, including accuracy up to 0.25 degree, maximum jitter of 1 degree per second, drift of 0.03 degree per hour with 0.05 degree at the maximum, and transient response having maximum 15% overshoot, which decays to 0.1 degree within 1 minute. And then for attitude determination, we use ring laser gyroscope and sun sensors. The gyroscope will provide an inertial measurement system, while the sun sensor provides an external reference. The specification on the performance can be seen in the table on the presentation. So gyroscope has a drift rate of 0.03 to 1 degree per hour, while sun sensor has accuracy of 0.005 degree to 3 degree. The mass for gyroscope is maximum at 15 kilogram, while sun sensor is only 2 kilogram. The power is 200 for gyroscope at maximum and 3 watt for sun sensors. And then for the determination system, we have two mechanisms. The first is momentum management, which calculates the momentum of the spacecraft and balancing it within a prescribed limit. And the second is three-axis stabilization system, which is some kind of control loop system, which balances the balances the attitude of the spacecraft through several control actuators and sensors. And then the second part is about navigation system, which consists of orbit tracing, sun orientation modification, and orbit transfer. For orbit tracing, this is the flow chart of the process, which starts from location determination and ends with actuator execution. And then sun orientation modification is used to acquire the sun and for reacquisition of the sun during emergency procedures. So the aircraft will measure the orientation towards the sun and will try to correct it should any error occurs. And then the last is orbit transfer, which is done to transfer the orbit during the launching phase. And then for components involved, we use three main types of components. The first is sensors, consisting of ring laser gyroscopes and sun sensors. And then the processors, we use attitude control unit computer, which will do the calculations on the control. And then the actuator consists of reaction wheels to generate momentum and thrusters to generate moments should some emergency case occurs.
For power system, the design requirements and objectives should be the power regulating function of the solar array must be accomplished without the use of the spaceship battery or auxiliary power supply, which may have intrinsic protective circuits of their own. And second, that any solar array power in excess of load demand shall always be autonomously prioritized for spacecraft battery charging without the requirement for intervention by any other spacecraft system. The power subsystem provides regulation, protection, and distribution of 1500 watt of solar array power, and it is supported by two 28 nickel cadmium batteries The main spacecraft power bus is regulated to 28 volt plus minus 1% with a 3-domain regulation, which is a solar array shunt mode, battery discharge, and battery charge mode. All power lines in the power subsystems to users are protected by LCL or latching current limiters, which protects the spacecraft bus. It provides temporized protection, it controls inrush and limited overcurrent, and it will avoid high current surges. The figure on the left is the solar array, and the figure on the right is the LCL or latching current limiters. So each LCL has decentralized undervoltage protection, allows the automatic switch off if the input voltage falls below 23.5 volt plus 1 volt. In the case of a main bus under voltage, the system will enter a safe mode that will turn down all the LCLs until the main bus will recover. In addition, foldback current limiters for some essential loads are provided, which is regulated battery power for the Kevlar cable cutters. All operations of the electrical power subsystem are redundant, including connection redundancy from the solar array and battery inputs to the power distribution outputs. The highest recharging rate that could be ordered is 1 amp or C per 20 for the batteries. During the initial attitude recovery phase, a power budget analysis revealed that the batteries could only be recharged at this 1 amp rate for 45% of the rotation period. And there is a positive energy balance, which could only be achieved if the total spacecraft power consumption remained under 67 watts. Because activating the telemetry and transmitter systems resulted in a 105 watt power bus load requirement, it was agreed that the system would only be triggered for snapshot telemetry on a regular basis.
Next is payload. For requirements and design objectives, there will be 6 aspects. The first one is mechanical architecture, where it provides a convenient way to access the payload instruments while maintaining the functionality of the instruments regarding its POW clearance, straight light avoidance, pointing stability, and waving direction. Next is thermal architecture. It maintains an acceptable temperature for all PLM and SVM modules mounted on the structure. And then there's electrical architecture, where it generates and distributes sufficient power to all instruments needed for the mission and able to handle the SVM and PLM modules. Next is communications. It will be able to efficiently transmit telemetry data to ground, that is able to ensure an RF and omni coverage to the users of high gain and low gain antennas. Next is dynamics and control, where it's able to accurately point the spacecraft optical reference axis to the sun, able to perform orbit maneuvers, and able to control the roll angle around the sun pointing axis. Lastly, its cleanliness. So venting and thruster position design needs to be considered. This is due to some instruments are generally sensitive towards contaminations. Next. The various instruments and its coverage are provided on the right side, the table on the right side, where there will be 12 instruments where each of the instruments has its own function for the mission. The detail way are only provided for 4 instruments due to some of them are not available on the internet. Next. The thermal control, there will be MLI, radiators, heaters, thermistors, paint, optical bench, panels, and sun shields. So we're using classical thermal controls. And then the paint, it will be black paint with different manufacturers and different application regions, which is on the right side of the table. And the enclosure of the sun shields are provided on the right side, the figure on the right side. Next. Lastly is the thermal balance and analysis. There will be 4 tests conducted for thermal balance, where each of them have different cases. The results are shown in the table below. Next. This is to increase the accuracy of the data. We changed the effective absorptivity into 0.085 and sink temperature 188 Kelvin, and the sufficient solar intensity is around 1450, and we incorporate the sensors and the spacecraft into the mathematical model, and we get this delta temperature between measured and predicted, which is around plus and minus 8 degrees Celsius, which is good enough, which is very accurate. Next.
Okay, so for the telecommunication section, we have a design objective of 8 hours during which real-time communication is foreseen with the ground system, 3 periods of 3.73 hours during which no communication with the ground is foreseen and onboard recording is performed, 3 periods of 1.6 hours with real-time communication, during which the previously recorded data will be dumped to the ground. The halo orbit requires that the high-gain antenna be capable of pointing in all directions within a plus-minus 32 degrees cone. And the satellite is designed to constantly transmit 200 kilobits of data via NASA Deep Space Network to Earth's ground station. Okay, next. So for the antennas, the design satellite is tracked using a 26-meter diameter antenna from the NASA's Deep Space Network. The links between the spacecraft and the ground will be provided by an S-band radio frequency system with duplicated receivers and transmitters. RF coverage is provided by a pointable high-gain 0.8-meter diameter antenna and 2 low-gain antennas to ensure the full coverage. And the halo orbit requires that the high-gain antenna to be capable of pointing in all directions within a plus-minus of 32 degrees cone. Next. So for the link budget calculations, we have the satellite data as follows. And the calculated transmitter antenna gain has a value of 22.72 decibels with an antenna transmitter loss of 0.5 decibels, an antenna beam width of 11.93 degrees, and the misalignment of 15 degrees. And therefore, we can apply the alignment loss of the transmitter being minus 18.96 decibels. And the calculated equivalent isotropic radiated power has a value of 11.04 decibel watts. Next. So for the losses, we have a propagation path length of 1.5 million kilometers, which causes space loss as much as minus 219.05 decibels, with an atmospheric loss of 0.1 and a polarization of 0.3, and we have a total loss of minus 222.15 decibels. Next. For the receiver antenna, we have a receiver antenna of 26 meters diameter, and the calculated gain is 52.24 decibels with a receiver loss of 0.5, and with a calculated beam width of 0.4 degrees and a misalignment of 0.5 degrees, we have a receiver antenna alignment loss as much as minus 18.86 decibels. And therefore, the calculated total receiver gain has a value of 32.88 decibels. With the sky noise temperature of 60 kelvins and the receiver temperature of 120 Kelvin, we can also calculate the system noise temperature of 180 kelvins. Next. For the powers, we have a power flux density of minus 183.51 decibels with a carrier power received as much as minus 178.23 decibels. With a noise spectral density of minus 206 and a carrier to noise density of 27.82, we can count from the data rate of 200,000 bits per second that the EV per NO has a value of minus 25.19 decibels. Next. So for the telemetry, we have the acquired satellite orbit data as follows. Next. So due to lack of data, we've been using the CubeSat link budget as a reference as an example for the telemetry channels being used with the following configurations. And the calculated rate collected on orbit will be as much as 1018.44 bits per second. Next. And the following is the calculation for the required downlink, the estimated daily downlink, the required telemetry buffer, and the required transmitter power for the satellite. Okay, next. So for the mission command, while the main ground station for the Deep Space Network is located in California, Madrid, and Canberra, the design satellite mission control is planned to be located at the Goddard Space Flight Center in Greenbelt, Maryland. While the data handling and processing, the satellite is designed to constantly transmit 200 kilobits of data via NASA Deep Space Network to Earth's ground station, while data handling is done by a 16-bit computer, MAS281, being installed in the probe. And that's all for our presentation today. Thank you.